Oh, we're doing that one. No, not 20. Oh, we're doing that one.
Yes, that one.
That one.
Not that one. The one in the picture, not the one on the dash.
Okay. Got it.
Jeez, yeah. Come on.
I'm sorry.
Amy, who should we have put up a free body diagram?
Michael.
What?
Michael.
Michael, put your free body diagram on the board.
All right. This is the math. No, it's not my
No,
favorite.
not yet. You couldn't get rid of
I accidentally
Rick
hit
Stan and Iron Ring because you're free body.
the other day, so I was trying to pull my blanket and I was gonna take it off, and I went, smacked this little forehead.
Yes. Just leave it like that without the notation, without the note. Erase the notes. That's fine. Everybody good so far? Just go adjusting what you've got. Okay. Let's see here. Anybody disagree with Amy's value for the weight of the hanging mass and binder clip? We good with that?
Yes.
Okay. How did we do with the weight of the meter stick? Everybody good with Ashland's value?
Yes. Where's the uncertainty?
Ooh, good question. I was thinking the same thing, but I can live without the uncertainty for this discussion.
I can't live without
But
it.
not for long.
I cannot live without it.
Soon you will need the uncertainty, just not yet. Okay, soon. All right, so let's see here. Next thing, Michael's free body diagram. Looks pretty good. Weight and normal force. All right, so let's ask this question. What's the value for, okay, let's see here. Who did we pick on last? Michael, who should we pick on now? Richard, what's the value for the weight vector that Michael has on there?
It should be whatever we got for the weight up there. For the,
Yeah, I'd like an actual number.
Oh, 2.23 newtons.
Okay, 2.23 newtons. Everybody good? Okay. Richard, who should we pick on now?
I don't know. Kim?
Kim. What is the value for the normal force that Michael has on his diagram?
2.23. Negative? Oh, newtons?
There we go. Okay. So they both have a magnitude of 2.23 newtons. I still have an issue with what Michael has drawn there. Though Michael, to his credit, would have fixed that, but I told him not to. Okay? So let's deal with this problem right now. It looks to me like Michael has the weight acting right about here, and the normal force acting right about here. Everybody good? And the weight is acting down, and the normal force is acting up. What would happen to the meter stick if the normal force acted up right here and the weight acted down right here? There we go. It would rotate. So, up until this point, you haven't had to worry about where forces act. I'm afraid that time is over now. Now you have to pay attention to where forces act. So that having been said, even though I know Michael already has this figured out, I want you to take about a minute maybe, talk with the people at your table, and determine what is the only location that we could have both forces acting, or what is required for the location where both forces act, so that the meter stick doesn't rotate. What's necessary for where those forces act so the meter stick doesn't rotate? Go.
Yeah.
Middle.
Usually, where I would be down
Like this?
yeah, maybe like that. That makes sense. But they would have to be like this.
Yeah, if I don't have to
Right.
do it.
Hey, coincidence is correct, but you know. Trust me from engineering school, sometimes that's helpful.
Yeah.
Just a line. Is there any like
Just like move one.
snow outside or at least help us go?
At this point,
Is this gonna be grand?
no.
You wanna help us pour buckets of water outside?
Opportunity for snow is gone. What you needed to do was go find a new superintendent's house last night about 3 a.m. and turn on the sprinklers.
Yeah, they tweeted at like
That might have
3:30
gotten us
a.m. I
out.
was like, what the heck?
Okay, we fooled around long enough. What is required for where those forces act if the meter stick is not going to rotate? Who can tell? Who cannot tell us that? What tables do not have an answer?
They have an answer. I don't understand.
They have an answer, but you don't understand. Okay, so Patrick, tell us what the answer is. And then John can explain it for us.
It's like in the center?
Okay, in the center. That will work. It's not necessarily the requirement, but that will work. Joanne, why is that?
Well, they both have to be acting on the same location on the meter stick, otherwise it's gonna rotate.
There we go. They both have to be acting the same location on the meter stick. As long as you got that for an answer, you have the correct answer. If the weight acts down in the middle and the normal force acts up at that same point, there's no rotation. Everybody okay with this idea so far? Any questions about this? Keaton?
For notating that, if we use one line segment and then put an arrow on both sides,
Or you could put one above the meter stick and one below the meter stick?
but could I do?
Could you do the other thing as long as I figure out what it is you're doing quickly? Because remember, anything that slows down my grading costs you points.
Right. So that way.
Yes, so the other way. There we go. Everybody good with this so far? Any questions about this? All right, so here's the other thing. What value did you guys get in your data? You got your data back with grades on it, right? Where was the normal force acting on your meter stick?
50 plus or minus 0.5 centimeters.
Okay, there's Colin's answer. 50 plus or minus how much?
0.25.
0.25. Okay, so 50 plus or minus 0.3 centimeters. Everybody good? Okay, what else do we have? Anybody got anything different? Keaton, what'd you guys get?
50 plus or minus 0.3.
Michael, what'd you guys get?
50 plus minus 0.2.
Joanne, what'd you guys get?
50.5 plus minus.
Sheridan, what did you guys get? For where the meter stick balanced in part A. With no weights on it. 49 prime. So, all the values that we've had encompassed 50 centimeters. Everybody okay with that idea? So here's my point, okay? Here's what we...
Remember to do attendance.
Thank you, Kim. This is an important job. I get in trouble with Dr. Pointer if I don't take attendance. Then I annoy him because I say, get lost. I've been here way longer than you. All
It's on
right.
video, Mr. Lyon.
So here we go. 50 centimeters, which happens to be the geometric center of the meter stick in this particular case. So there is some vocabulary you need to make sure you understand. First of all, since 50 centimeters is essentially where the ring stand acted, it's also where the weight, according to what you guys just told me, also had to act, right? So the weight of the meter stick essentially acted at 50 centimeters. What do we call the position where an object's weight acts? Keaton?
Center of mass?
Close.
Weight.
Fulcrum.
Not necessarily.
No, I don't know.
Center of gravity. Okay, Keaton, the center of mass is usually also the center of gravity, but with some extended objects in some really different circumstances, it's not the same exact place. A little annoying, but okay, whatever. Okay, generally it is though. Okay, so center of gravity. In this, so there's the first thing. The position where the weight acts is called the center of gravity. That's one piece of vocabulary you need to understand, because we're going to use it a lot. Next thing you need to understand, it turned out that the center of gravity for your meter stick was also the geometrical center. Everybody okay with that idea? What that means is that the meter stick is what we refer to as uniform. For the center of gravity and the geometrical center to be the same place, the distribution of mass throughout an object has to be the same. That is, if I pick one particular section on an object and another section with the same volume, they'll have the same mass. So if I look at these two 10 centimeter sections at the very ends of the meter stick, same mass. This 10 centimeter section and this 10 centimeter section, guess what? Same mass. And this one, okay, all of these 10 centimeter sections have the same mass. All these 1 centimeter sections, same mass. That's what we mean by uniform. So when you see a problem which says the bridge is uniform, where does the weight of the bridge act? In the middle. There we go, at the center. Everybody okay with that? Now, a lot of objects, the center of gravity and the geometrical center don't overlap. Those objects are not uniform. Okay? Everybody good with that idea? And sometimes objects which look like they're uniform aren't actually uniform. Okay? So, for example, hey, Lonray, balance this on your finger. There you go.
Oh yeah, Lonray.
Oh, yeah, Lonnie.
Don't break it.
It's a tricky tool the other way.
Lonray, you're not balancing it in the middle. What's wrong with you? There we go. Yeah, Mr. Lyons drilled out one and filled it with lead. Yeah. So there we go.
Be careful,
Not the
Andre,
same.
lead is poisonous.
Okay.
Be careful.
Yeah, that's poisonous. Or
It looks like a wand.
this one. Yeah. Here you go, Daniel. Balance that for us.
It's Hey, Expelliarmus, Daniel.
Hey, you're not in the middle. Yeah. There's like, yep, sure enough. Why not? Right. The two balls that look the same on the ends at first glance, this one's hollow and cardboard, and this one's solid and wood. Yeah. Okay? So uniform is an important term for you to recognize. It means the weight acts right in the middle. Okay? The geometric center. Everybody okay? Okay. By the way, what symbol do we use for center of gravity? A couple of them that you need to recognize. Brandon?
No, I was not raising my hand. I was.
Too late now. It looks like it's up.
I was trying to.
Guess a letter.
CS. I don't know.
Really close, actually. Center of gravity.
Actually, it's coming to me. C subscript G.
No subscript, just CG.
CG. Sorry.
Yeah.
That's okay.
Okay, CG, or we also sometimes use this symbol.
No, you know what? You can't catch to save your life.
Wow. Bro.
That's rude. You can't. How do you know that?
That's the other symbol we use.
Yeah.
Why? Because we do. That's been the symbol for center of gravity long before it was the symbol for BMW. Which before it was the automobile symbol, it was the aviation.